The purpose of this screencast is to demonstrate matrix multiplication and how to use it for encryption and decryption with the Hill cipher. We will be restricting our attention to using 2x2 and more generally 2x(n) matrices, although the general principle can be extended to larger matrices. We will start with the following two matrices. To concentrate on how matrix multiplication works and for the sake of clarity, for this first example, we're not going to worry about working mod 26. Alright, so we want to multiply these two matrices called K and B. The reason it's called K, this is going to be a key matrix later on in a Hill cipher example, so I thought I would start calling it K to begin with. Okay, in order to multiply them, the first thing I need to do is compare their sizes. I have a 2x2 for K and a 2x4 for B. I can multiply them because these two values, those two 2's, are equal. In other words, the number of columns of K is equal to the number of rows of B. Alright, because I can multiply them, then the outcome is determined by the external indices. So I'm going to get a 2x4 matrix when I multiply them. Okay, so KB is going to be a 2x4 matrix, and I will fill in the entries as we go. The general principle is that we use the rows of the first matrix and the columns of the second matrix. So we'll use the rows of K and the columns of B. We move across the rows of K and down the columns of B. To find the entry in the IJ position, I use row I of K and column J of B. So if we wanted the 2-3 entry of the product, I would use the second row of my first matrix and the third column of my second matrix. So we will start with the 1-1 entry. Okay, so first row, first column. I'm going to use row 1 of K and column 1 of B. We multiply corresponding entries and add them together. So I take the first entry of this row and the first entry of this column, and I multiply those together, and then I add to that what I get when I multiply this entry of the row and the second entry of the column. So my 1-1 entry is going to be 1 times 2 plus 2 times 3. So 1 times 2 and 2 times 3, otherwise known as 8. Alright, so that takes care of the 1-1 entry. Alright, now I'm going to move across the rows. I could go down the column if I so desired, it's personal choice. Alright, so to get this entry here, I'm going to use the first row again, and now I'm going to use the second column. So I will get 1 times 1 plus 2 times 4. And that gets me 9. Alright, and then lather, rinse, and repeat. I'm going to take 1 times 4 plus 2 times 1, and I get 6. Alright, and then finally I'm going to take 1 times 1 plus 2 times 2. 1 times 1 plus 2 times 2, which will be 5. Alright, that gets me the first row of my product. So now, to do the other row, I'm now going to switch to the second row of K, and I'm going to repeat the procedure with each one of the columns of B. For the sake of not boring you to tears, I am not going to narrate this as I do it. I'm just going to sort of work it out. I might mutter under my breath as I do the multiplications. 1 times 2, 1 times 3, alright, again. Oops. Alright, and then 3 plus 4, that's 7, and then 12 plus 1, that's 13, and then 3 plus 2, that is 5 again. Okay, and so there we get our matrix when we multiply K times B. Now, note that if we tried to reverse them reverse the order and work out b times k, well, then I would have 2 by 4 multiplied by a 2 by 2, and this number don't match. So because of that, our little method just won't work. So in this reverse order, there is no defined product, and I can't multiply those two matrices. Okay, the next thing we need to worry about is matrix inversion. All right, so to invert a 2 by 2 matrix, we start with this general form, A, B, C, D. The first step is to compute what's called the determinant, which is this quantity here, AD minus BC. If this number is not invertible mod 26, then the matrix cannot be inverted. It's just not going to happen. All right. If this number is invertible, then we're lucky in the case for 2 by 2s, there's a nice compact formula for finding the inverse. Namely, A inverse, I take that determinant, I take its inverse, and I multiply it by this matrix here. I get to this matrix by taking my original matrix, I reverse my diagonal entries, and I negate my off diagonals. We're working mod 26, so when I'm all done, I would then reduce it mod 26 so that I would get values between 0 and 25. All right, so for an example, let's look at this matrix A here. Okay, so the first thing I need to do is work out my determinant. So my determinant is 1 times 9, A times D, minus 2 times 3. All right, it gives a value of 3, which is definitely invertible mod 26 because it's odd and not 13. And if we need the inverse, if you don't remember it, we can always use power mod, and we get an inverse of 9. Okay, so my inverse, I'm going to multiply the whole matrix by 9, and then I'm going to use this formula here. So I'm going to reverse these two entries. So I'll have a 9 here and a 1 there, and then negate the off diagonals. Now, I take everything in this matrix, and I multiply it by 9. Gets me 81, negative 18, negative 27, and 9. All right, but now we are working mod 26, so I'm going to reduce all of those mod 26. See, off the top of my head, so 78 is a multiple, so that becomes 3. If I take negative 18 and add 26, I get 8. Negative 27, add 52 to that, get me 25, and 9 stays alone. Okay, so this would be my inverse. We now turn our attention to the Hill cipher. In the Hill cipher, we parse the plain text into a matrix and then multiply by a key matrix to encrypt, all while working mod 26. For our example, we want to use one of the earlier matrices as a key matrix, namely this one here. All right, to begin with, we're going to encrypt simply the plain text telephone. All right, so the first thing I need to do is convert it to numbers. Now, the Hill cipher is polygraphic. More to the point, it's digraphic. You're going to encrypt pairs at a time. So pairs of numbers go in as the columns of the matrix. So my first column would consist of 19 and 4, and then 11 and 4, and then 15 and 7, and then 14 and 13, and then 4, and unfortunately telephone has an odd number of characters, so we just throw on a random character. I'm essentially going to throw on the letter X. All right, and now we have to multiply the two matrices together, this time working mod 26. All right, so we just multiply these like we did the previous example. I'm going to use the rows of the first matrix and the columns of the second matrix. All right, I will do maybe a few of the entries. I'm not going to narrate all of them. It would take too long. So to begin with, again, I take first entry, multiply by first entry, second entry by second entry, and I add those two together. So that's going to get me 27. All right, to make things a little different, last time I went across the rows, maybe this time I'll go down columns. So to get this entry, I'm going to take 3 times 19 and add 1 times 4. So 3 times 19 plus 1 times 4. All right, now we are working mod 26. I'm not going to worry about that just yet. I can reduce mod 26 whenever I want. I will do that when I'm all done with the matrix multiplication. All right, so for my next column, I'm going to again use my first row, second column. So I'm going to get 11 plus 8, which is 19. All right, and then second row, second column. So 33 plus 4, that should be 37. All right, and then 15 plus 14, that will be 29. And then 3 times 15 is 45, plus 7, and that's 52. All right, I'm just going to fill in the rest, which I've worked out off screen. Okay, and now I need to reduce this mod 26. So I should have put in an matrix earlier, so I'll put it in now. 2 by 5, that's what I need. All right, and so now I just go through and I reduce everything mod 26 as needed. So that's going to be 14, this will be 2. 61, that's going to be 9. 61 minus 52. 37 minus 26, 11. 52 is a multiple of 26. That will be 3, and then this will be 11. Okay, so this is my cipher matrix that's come out, and now I need to turn it back into letters. So do the same thing as I did when I was putting it into the plain text matrix. I put in my plain text as columns. I'm going to read off by columns. So it will be 1, 9, followed by 19, 11, followed by 3, 0, 14, 3, and 2, 11. And there is our ciphertext. All right. Now for decryption. Mechanically, decryption is precisely the same as encryption. The only difference is I am going to use the inverse of the key matrix in order to do the decryption. So we've got this ciphertext to decrypt. So the first thing we're going to need to do is figure out the inverse of our key matrix. All right, well, first things first, I work out my determinant. All right, which is -5, which is the same as 21 mod 26, which is invertible. And so to find the inverse, I need the inverse of 21, or the inverse of -5, they're the same number, mod 26. All right, which is 5, conveniently. All right, now I reverse my diagonal entries. My diagonal entries are the same, so it doesn't look any different. And then negate my off diagonals. All right, and then multiply through. And again, I should have put 2 matrices. All right, and now I could use it like this, or I can reduce it mod 26 if I so desire. It's up to you. All right, so if I did reduce it mod 26, I would get 2 rows. All right. Okay, so the 5 and the 5 clearly don't change. Negative 10 plus 26 is 16. Negative 15 plus 26 is 11. All right, so this is the inverse of K, and that's the matrix I am going to use in order to do the decryption. Now, one of the reasons that I might not have reduced it mod 26, because I could have done that at the end, it might be easier to multiply by negative 10 than positive 16. We'll see. All right. But I undo it, or I decrypt the same way I encrypted. So in particular, again, my numbers go in as pairs, as columns. So I'm going to get 10, 10, and then 7 followed by 18, and then 16 followed by 19, and then 8 and 17. Now, I have either missed something or I didn't realize 1, 2, 3, 4, 5, 6, 7, 8. No, okay. This is only a 2 by 4. All right, so I'm going to have an extra column here just from my formatting. All right, so now I start multiplying them just like I did before. The numbers are going to get a little hairy, but oh well, such is life. Okay, so I'm going to take 5 times 10 plus 16 times 10. All right, so that's 50 plus 160, which is 210. All right, and then 110 plus 50, that's 160. All right, and at this point, I'm just not going to pretend. 5 times 7 plus 16 times 18 is 323. All right. And then 11 times 7 plus 5 times 18, 167. All right. And then I just keep going. Alright, and now 5 times 8 plus 16 times 17, 312. Okay, 173. Okay, so there is my first matrix, and now I need to reduce that mod 26. All right, and I'm not even going to pretend. I'm just going to feed all the values. I'm going to do each row separately, just so I don't get confused. And that's 3, 4, 12, reduce mod 26. All right, so 2, 11, 20, 0. All right, and then I'm going to do the same with the second row. 16 plus 116, followed by 167, 271, 173, on 26, 4, 11, 17. Okay, so there is our plain text matrix. And lastly, I send it back to letters, and again, I read down my columns. And we hit cellular. All right, so there's an example of how to use matrices in the Hill cipher and their multiplication and their inversion.